In our first example in section 2.3, we're going to look at what happens to a square under a translation. Translation in question is going to be of the form z plus 2 minus I. So this translation shifts the real part over by 2 and shifts the imaginary part down by 1. And our square, which we're going to call S, has vertices at 1 plus I, 2 plus I, 2 plus 2I, and 1 plus 2I. So if we were to graph our square just quickly, we would have to go up to 2 and then go over also to 2. So we have 1 plus I, 2 plus I, 2 plus 2I, 1 plus 2I. So here's our square S. Now, we could sit here and we could parameterize the sides of the square. And then compute the image of the parameterizations, as in the previous section. But when we have nice functions like linear functions, which is what this is. This is not necessarily a linear function, but it preserves linear objects. It's a Euclidean isometry. What we can do is we can rely on the fact that these rigid motions or these isometries, they preserve linear objects. So instead, we're going to use that these linear mapping. I'm going to put linear in quotes. This is technically affine. It's affine. Well, I'm not even going to write that actually. We're just going to say isometries. Of course, if you just add 2 minus I everywhere, you're not stretching anything. Instead, use that isometries preserve linear objects. They also preserve circular objects. Anyways, since they preserve linear objects, to figure out where the square goes, we don't have to figure out where all of the points go. We just need to figure out where the vertices of the square go. And then once we know where the vertices go, we just have to connect the dots. So it suffices to compute the image of the vertices, which is t of 1 plus I, t of 2 plus I, t of 2 plus 2I, and t of 1 plus 2I. And remember, t is the translate by 2 minus I function, so all we're going to do is we're going to add 2 minus I to these. So we get 3, we're going to get 4, we're going to get 4 plus I, and we're going to get 3 plus I. So we have to add 2 to the real part and subtract I from the imaginary part. So the image of S, we have to go all the way over to 4, it looks like, is also a square, and it has vertices at 3, 4, 3 plus I, and 4 plus I. So here's our S prime. This is T of S. So these translations, but we'll see in a little bit how to express other Euclidean isometries or non-isometries but linear, like scaling. They have a pretty clear effect on things, and so we don't have to rely on parameterizations necessarily to compute images of curves or regions.